Good afternoon, everyone. I hope my voice is audible to you and my slides are visible to you. So, I welcome you all to the fifth tutorial of this course, Introductory Organic Chemistry 2, which is conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Niraja Dashaputre from ISER Pune. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. So till now we have conducted 4 tutorials on this course on various topics where we have extensively solved a lot of conceptual questions and mechanisms. So this week's topic was enols and enolates and also introduction to aldol condensation reactions. So not much videos were there. A few videos were provided by Professor Harinath Chakrapani sir. I hope you have gone through those video lectures and I feel this week's topic was relatively easier. So we are going to solve a few conceptual questions in this tutorial on the same topic. Okay. So and also the recording of this lecture you will get on the YouTube channel Tutorials by Deepika. If you by chance miss any concept or miss any questions description, you can again go through the recording. Okay, so let us move to today's lecture. So the first question of today's tutorial, which of the following is the structure of the most stable enol form of 2-methyl pentane 3-one? So this is the structure here which is given. It is 2-methyl pentane 3-one. Okay, just in the answers if you see, the structure is, you can say, 180-degree rotated, but that is not our concern. This is basically the structure of 2-methyl pentane 3-one. So in the question they're asking, if you visualize the enolate form of this ketone, which one out of these 4 will be the most stable enolate form? Okay, so this particular structure, if you look at the structure, you have 2 possibilities from through which you can generate the enol of this ketone. Okay, one is this has alpha hydrogen, and the other is this one also is containing alpha hydrogens, okay, alpha protons. So you can either get the enolate form via this side of the ketone or via this side of the ketone. Okay, so when it comes to stability of enol forms of ketones, you have to look at a few factors, out of which the dominating factors are number 1, the enol double bond should be most substituted one. Okay, if you have possibility of various enols, the one in which you will have the most amount of substitution, the highly substituted one enol will be the most stable out of all. That is one factor. Number two factor, you have to also look at if there is a possibility of hydrogen bonding stabilization in your substrate. In this one, of course, we do not have such possibility. In the coming questions, you will encounter that in a few structures or substrates, you will have the possibility of hydrogen bonding stabilization for the enol. In that particular case, we will choose the enol as the most stable one where we are getting hydrogen bonding. Okay, these two factors are the most predominating factors in case of stable enols. So in this particular question, we just have to look at the option where we are getting the most stable enol with the most amount of substitution present in the double bond. So if we look at the number option A, yes, it is the highly substituted enol that is possible. Otherwise, if this double bond is in this side, that will be a tri-substituted double bond. But in this case, we have a tetra substitution on the double bond. And then the option B is just now whatever I said, the second option where you get the tri-substituted one. So this one will be less stable over option A. We already know that. And then again, option C is basically the stereoisomer of option B. Just it is the Z isomer. Okay. So, sorry, the E isomer. Okay. This is the Z of this structure and this is the E isomer. So, we will cut down these two possibilities because in these cases we are getting tri-substituted double bond. So, we are left with option A and option D. Now, you just have to look at the other factors which can account for the stability of enol. That will come from the steric factor. Okay. Out of these two possibilities, whichever is sterically more stable or sterically less hindered, that enol will be the most stable enol form of this particular compound. Okay. So to choose this one, in option A, you can see that this hydroxyl group and the methyl substituent on the other side are in cis, and this methyl and this ethyl is cis. But in option B, we get that this ethyl group is coming in a cis manner. Okay, actually this option D is not even the structure for the given question. Okay, these two, out of these two option D is not even the structure of the given compound. Okay, so we are definitely left with the option A. Okay, and this note you may have already studied. In this one, it is summarized that what kind of enol products you can get under thermodynamic conditions and under kinetic conditions. Okay, so what happens when you are using sterically bulky bases? You will observe the formation of the kinetic enolate. And when it comes to less sterically bulky bases, you will observe the thermodynamic enolate formation. Okay, this you can note down because we will encounter these two preferences, which one to choose when we are going to solve the next coming questions. Okay, so for example, you can talk about when it comes to LDA or butyl lithium. In those cases, we always observe the formation of the less substituted double bond in enolate. This is due to the steric hindrance of the base present. Okay, and when it comes to the bases of potassium hydroxide or sodium hydroxide, in those particular cases you do not have the steric hindrance factor, so you get the more substituted double bond. Okay, so the option A was the correct answer for this question. where we had the tetra substituted double bond. Okay, so the next question is also similar. In this one, you have which enolate derived from 1-phenylbutane 2-one is most stable. Okay, this is the compound, and again here also you have two types of alpha protons where you can generate the enolate of this structure. So after these four, you have to choose the one which is the most stable. Okay, so in option A, you can see that the enolate we are forming in this way. Okay, in terms of substitution, you can see that in both sides you will get the similar kind of substitution on the enolate double bond. Okay, in both the sides you will get tetra substituted double bond. But what happens if the option A forms, then the conjugation with the phenyl ring will be absent. Okay, and we want conjugation for the stability. If we have a possibility of forming the enolate where the double bond forming in a conjugation with the phenyl ring, then that enolate will be most stable. So we will not prefer option A as the right answer. Okay, again option B is also just the substituents have been reversed in their position orientation. So option B also we can cancel out, because here also we are not getting any conjugation with the phenyl ring. So we are left with option C and D. Okay, and both these are the structures of enolates, and both of these will form in the reaction. Okay, but one of these will be major in the reaction mixture. So how to determine which one will be more abundant in the reaction mixture? For that, I hope you have already understood that this double bond in these two structures are in conjugation. Okay, so definitely one of these will be major in the reaction mixture. Now you have to look at the steric factor. You have in this particular double bond, you have an aryl substituent and an alkyl substituent. Okay, here also you have aryl and alkyl substituent. So if we place this alkyl substituent with the phenyl ring, these two will have steric hindrance. Okay, that is why option C is found to be abundant in the reaction mixture. Okay, so this is the explanation, the brief explanation. Like I said, that in this particular structure, where the phenyl ring and the alkyl chain is anti to each other, will be the less sterically strained product, and that is why that will be the more abundantly formed in the reaction mixture. So this will be the most stable enolate form of the given compound. I hope that was clear. So again, this is also the same concepts question. Which enol form of the following dicarbonyl compound is predominant and at equilibrium? So this dicarbonyl compound is given. Here you have again two possibilities. One is this and one is this, via which you can form the double bond, isn't it? So we will look at the options one by one, which particular form will be formed predominantly. Okay. So in option A, we are forming the enolate in this side, where we are getting a di-substituted double bond. Okay, and on this direction of the double bond, it contains no substitution. Okay, and then in option B, we are forming the enolate here. Okay, so if we are forming the enolate here, we are getting tri-substituted double bond. Again, option C is structurally it is quite similar as B. It is just the stereoisomer. So here also we are getting the tri-substituted double bond. Okay, and For option D, it is not the enolate form of the ketone, okay, this ketone. So for this ketone, if we have to form the enolate of this, most acidic protons are present either here or here, and it will move towards the electron deficient carbonyl group. So option D you will not observe as the enolate form of this dicarbonyl compound. Okay, so we are left with option B and C to be the most stable one, because this, which what was the first factor? It has to be the most substituted one, isn't it? So out of option B and C, any one of these two will be more stable. So we will figure out which one will be the one and why. So if you look at the structures of these two, in this one, the hydroxyl group is present in the same phase as this carbonyl group. So in turn, what you will observe, that you will observe hydrogen bonding between the hydroxyl group's proton and this carbonyl group's oxygen. Okay, it will kind of form a six-membered ring which is stabilized by hydrogen bonding. Okay, you can observe the hydrogen bonding between these two functionality. But in terms of option C, no such hydrogen bonding stabilization is observed. Okay, because it is on the opposite face of the carbonyl group. That is why when it comes to option B and C, B will be the major enolate. Okay, this one is actually the description. You can note it down, whatever I have explained for this one. So since option B we are observing hydrogen bonding stabilization, this will be formed as the major enolate. Okay, the most stable enolate at equilibrium. I hope this was clear. With this, we will move to the next question. Okay, which combination of carbonyl compounds gives phenyl vinyl ketone by an aldol condensation? So till now we are familiar with the concept of enolate, stable enol, stable enolate formation. So we will see now, out of these four reactions given, which combination will give us the formation of phenyl vinyl ketone via aldol condensation. So I hope you are familiar with aldol condensation already. Uh, Still, let us revise the mechanism once. What happens for aldol condensation? We will need at least one substrate which is containing an alpha hydrogen. Okay, alpha hydrogen to the carbonyl group. So in the first step, the base which is used in the reaction will abstract the acidic alpha hydrogen from the carbonyl compound, and in turn you will get this carbanion generation. Okay, and then in the subsequent step, this carbanion will attack at the carbonyl group of the second substrate, and it is not necessary that the second substrate will also contain alpha hydrogen or not, because we will need at least one substrate which is having alpha hydrogen for the generation of this carbanion in the first step. Okay, so in the second step you will observe the attack of this carbanion on the carbonyl group of the second substrate, and then what happens, you will observe this formation of oxyanion. Okay, as a result of this nucleophilic addition reaction, you will observe the formation of this oxyanion, and you have already water in the medium because we use aqueous base in the reaction. So from the water, the oxyanion quickly picks up a proton to give you this beta hydroxy aldehyde. Okay, so after the formation of this hydroxyl group here, in the last step of aldol condensation, you have to remove a water molecule. Okay, In condensation reactions, we remove small molecules, usually commonly water. So in aldol condensation, in the last step, you will observe dehydration to, to get alpha beta unsaturated aldehyde or alpha beta unsaturated ketone. Okay, so like this, in the given question, we have to now apply aldol condensation on all these substrates given. So if you look at the product phenyl vinyl ketone, you have a double bond here, which must be generated in the last step like we observed in the mechanism, isn't it? So if we have obtained this double bond here, in the third step, what we observed, we got a beta hydroxyaldehyde, isn't it? So for this ketone, we have to place a hydroxyl group in the beta position if we want to know the third step. Okay, so here we will get a hydroxyl group and here you will get a hydrogen. So now you already know that out of these four combination, which which combination will be the one which will give you a hydroxyl group here in the third step. Let us go one by one through the options. For option A, suppose we are generating a carbon ion here because it is containing alpha hydrogen. After generating a carbon ion here, if it attacks at this formaldehyde molecule, yes, you will get a CH2 and then CH2OH group after the protonation step, isn't it? So yes, it is matching with the product that we can obtain in the third step. Okay, let us keep option A in our hand. If it comes to option B, after the generation of carbon ion here, if it attacks at the aldehyde here, you will get a methyl substituent vicinal to the hydroxyl in the third step. Okay, but we do not need this methyl group. So option B we can cancel out. For option C and D, you can see we do not have alpha hydrogen attached to this first substrate. Okay, we need alpha hydrogen attached to this first substrate. Okay, but we do not have it. Even if we consider option C to give carbon ion here, then you will need an aldehyde. Okay, you will need the aldehyde intact if we form the carbon ion here, which is not possible for the formation of phenyl vinyl ketone. So we now are left with the single option, which is option A. Okay, because this is the only combination which was giving us a hydroxyl group here, like CH2 and CH2OH here, isn't it? So we will choose option A as the correct answer for this question. Option A is giving us phenyl vinyl ketone via aldol condensation. Okay, I hope this is clear. After that, let us move to the next question. And I find these arrow pushing questions very interesting because these play a major role in understanding the mechanisms of the reaction. So let us move to the next question. The following scheme shows a mechanism for the alpha bromination of a methyl ketone with bromine in ethanoic acid. In which stage do the curly arrows wrongly show the flow of electrons? Okay, this is a mechanism given for alpha bromination of a methyl ketone. Okay, we need substitution of one proton by a bromine here, and the condition given is bromine in acid. Okay, so we have to choose out of all these stages in the mechanism which stage is showing wrong flow of electrons. Okay, always while drawing mechanisms, we have to note down that electrons must flow from an electron rich source to an electron deficient source. Okay, because if we are sending electrons from a rich source to a rich source again, you will get a system of electronic repulsion. Okay, so always remember that basic concept. So in stage 1, what is happening? Protonation of the carbonyl oxygen. So this oxygen is having lone pair of electrons and it is electron rich. So for protonation, it is attacking the acidic proton of the ethanoic acid in the condition. Okay, so yes, after the abstraction of the proton, the leaving group OAC is knocked out in the first step. Okay, so yes, this stage is showing the flow of electrons correctly. Okay, and if then we come to stage 2, the knocked out OAC minus is now again abstracting an acidic proton from the methyl ketone. Okay, these alpha hydrogens are acidic in methyl ketone. So definitely these basic anion present in the system now will abstract a proton from here. As a result, you will observe this CH bond breaking, and the electrons from the CH bond will flow to this CC bond. Okay, and you will observe the formation of enolate by neutralizing this oxygen positive charge. Okay, so again in stage 2 also you are observing a correct flow of electrons. And then in the next stage, let us see. In next stage, we are observing that from the bromine Br2, first the Br2 bromine bond is breaking, and one bromine knocked out from the breakage is attacking at the double bond. And as a result, we are sending electrons towards the oxygen. Okay, so is this particular step possible? See, the carbon-carbon double bond is rich. Okay, why is it rich? Because it is having electron flow from the oxygen towards the carbon-carbon double bond. And this bromine atoms from generating by breaking of Br2 are actually electrophilic in nature. Okay, so it is already electron deficient. It is not possible to donate electrons from a electron deficient species. That too, we are donating electron to our electron rich double bond, which is again creating a destabilization due to electronic repulsion. So you can identify stage 3 as the wrongly shown mechanism stage. Okay, because this electron deficient bromine species is attacking a electron rich carbon carbon double bond. Okay, so we will keep the stage 3 in hand and move to the next stage 4, where what we can see, again this oxonium proton is abstracted by the knocked out Br minus, which will be forming as a result of the correct stage 3. Okay, this is a wrong stage, so correct, if we correct the stage 3, what will be happening? Electrons will be pushed from oxygen and this double bond will attack at the bromine and a Br minus will leave. So what happens in stage 4, that knocked out Br minus will take up this oxonium proton and neutralize the carbonyl oxygen. Okay, this stage is correct. And then in the last step, like as the final product, due to this proton abstraction, you get this alpha brominated methyl ketone. So after analyzing all the steps in the reaction, what we came to know? We came to know that stage 3 is the one which is not showing the curly arrows correctly. Okay, I hope this was well understood. And again, this description is here. It is written in stage 3, bromine is the electrophile and a lone pair on the oxygen of the hydroxyl group pushes the electrons. So the curly arrows show the flow of electrons in the wrong direction. Okay, so I hope this question was well understood. After this, again, a similar question is here. I think we have already solved this question. So I will leave it to you to solve. Which of the following is the most stable enolate derived from 4-methylhexane 3-one? Maybe not this particular question, but we have already solved this kind of question. You analyze the options and figure out which one will be the one and match with the option given here. Okay, you look at the options and check whether you are getting option C as the correct one or not. Okay, but this is a very stable uh, sorry very easy question after as we have solved option question 1, 2 and 3 already on the same topic. Okay, so moving to the next question. Which enol form of ethyl 3-oxobutanoate is predominant at equilibrium? Again, similar question has been solved, but still let us try to revise it again. What happens? 3-oxobutanoate. Okay, you just for the substrate here you will have a methyl and then here you will have the carbonyl group, and again in the same substrate we have two possibilities of forming the enolate. Okay, in this direction and also this direction. Okay, so which one will be the more stable? Definitely the one where we will get the highest substitution on the double bond. So if you look at option A and B, option B is giving you a tetra substituted double bond. So option A we will cancel out. Okay, and option B, out of option B and C, like we observed similar condition here also in option B, you can expect hydrogen bonding between the hydroxyl group and this carbonyl group of ester. Okay, so option B will be predominantly formed over C. And then like we saw in question number 3 or 4 where we had NME2 here also option D will not be the enolate form of 3-oxobutanoate. Okay, so since we are left with option B and C, you will see that B is the most stable one due to stabilization via hydrogen bonding. And this is the description. If you need, you can note down or maybe take a screenshot. So with this, let us move to the next question. Okay, which is the main product of the following reaction? Again, looking at the conditions, you have already studied extensively the topic aldol condensation. So this particular reaction is given will be aldol condensation. So if we carry out aldol condensation between benzaldehyde and acetone, what product will we get? Out of these 4 options, which product you will get as a result of aldol condensation? So here I have shown the mechanism for a reaction of benzaldehyde, okay, and acetaldehyde, but in place of acetaldehyde we have a acetone here. So for the final product you will observe here 1-methyl. Okay, otherwise the mechanism will be exactly same. Okay, like for this product here you will have a methyl for acetone. So let us briefly talk about the mechanism. What happens? The hydroxyl group will abstract the acidic proton from uh, acetaldehyde or acetone in case of the question, and leading to the formation of this carbon ion, which will be stabilized as its enolate form, and this enol will now attack at the carbonyl group of the second substrate. As a result, you will get this beta hydroxy group, and after the formation of this beta hydroxy group, you get dehydration for the formation of alpha beta unsaturated compound in aldol condensation. Okay, so out of these four options, which one will be the correct answer? Which one will be the one which is matching with the answer? You will see that C and D are matching with the mechanistic answer. But you have to see that C is a trans product or E product, and D is the Z product or cis product. And when it comes to steric stability, E product is always more stable over the Z product. Okay, E isomer is always the more stable one. So if you are asked what is the main product in the reaction, the more stable E one will be the correct answer. Okay, so this E isomer will be predominantly forming. Okay, this brief description you may note down, but I hope this was a very easy question. After this, let us move to the next question where we are going to discuss a few reaction conditions from the topic enol and enolate. Okay, and we will try to see which of these four reactions is showing the correct main product. Okay, only one out of these four reactions is showing the correct main product, and to figure out the correct option out of, in this question, you will need the help of the summary of kinetic product and thermodynamic product formed when it comes to enolization. Okay, so with that concept in our mind, let us move to this question. So in option A, what is it given? It is showing that two molecules of ET, you can consider, is taking part and undergoing aldol condensation, and the base which is given here is not sterically bulky, so you have to expect the formation of thermodynamic enolate here. Okay, and as a result you will get the formation of the most substituted double bond. But in the question, okay, in the question, if we look at what is happening, uh, from the answer given, you can see that this carbon, okay, this particular carbon is attached to the carbonyl group of the second molecule, where you are observing the leaving of ethoxide ion. Okay, that is not our concern, but just look at the carbon which is attached to the carbonyl of the second molecule. It is this one. Okay, it is the outer one. But is it the most stable acidic proton? No. The most not stable, most acidic. Okay, most stable most acidic protons are present here. Okay, in this CH2 group, it is containing the alpha protons of the carbonyl. So if we subject it to basic condition, abstraction of protons should take place from this particular carbon, not this. Okay, this is not possible, so the answer shown here is not correct. Okay, so moving to the next option, option B, where we are treating this methyl ketone to basic condition in presence of this bulky base. Okay, and these bulky bases like butyl lithium, LDA, or uh, these lithium bases. In these particular conditions, we observe the formation of kinetic enolate. And kinetic enolate is, you have to remember, the one which is least stable because of less steric hindrance, least substituted. Okay, so we have two possibilities here. One is this and one is this. Which one will be the least substituted one? The one which will be forming here. Okay, in case of this particular base, you have to get the formation of double bond here. But in answer, are we given that one as the option? No. Okay, in the option we are given the most substituted double bond, which is not possible in this base. For that, we need sterically less bulky bases like sodium hydroxide, sodium hydride, potassium hydride. All those bases will give you this more substituted double bond. So option B is also showing the incorrect main product. Okay, moving to the next option. Again, we are treating the same methyl ketone but in presence of different base this time. We are now using potassium hydride. And in presence of potassium hydride, you will observe the formation of the thermodynamic product. So this most substituted double bond will be formed in case of potassium hydroxide. So we know that option C is showing the product correctly. And if it comes to option D, it is actually showing a SN2 substituted reaction starting from an enolate. But does these uh, aryl halides undergo SN2 substitution this easily? No. Okay, substitution on phenyl rings do not take place under such conditions given. So you will not get the formation of this product under these conditions. Okay, uh, if you were given other conditions here, like for example, you can consider methyl iodide kind of substance, you would have observed the formation of such product. Okay, this O electron pairs would have been pushed and this double bond would have attacked at the methyl iodide, suppose, and you would have obtained methylation in the alpha position. But in case of aryl halides, such SN2 reactions do not occur. This is why option D is also showing the main product incorrectly. Okay, so option C will be the correct option, which is showing the main product correctly. Okay, under these basic condition, you will observe the formation of this thermodynamic enolate. Okay, I hope this was clear. And after these reaction studying, we will move to the next question. Okay, again, this is a mechanism based question. The scheme below outlines a mechanism for the synthesis of a ketone hex 5-2-one from ethyl 3-oxobutanoate and acetoacetic ester ketone synthesis. In which stage do the curly arrows wrongly show the flow of electrons? Okay, so we are treating this dicarbonyl compound and arriving at this ketone formation. Okay, so you have to choose the stage where the curly arrows are wrongly pushed. Okay, wrong flow of electrons are shown in which stage? Let us move one by one like we did in the previous question. So in stage 1, what is happening? This ethoxide in the reaction mechanism, in the reaction medium, will abstract a acidic proton. Okay, out of these two alpha protons, these protons are more acidic. Why is it so? Because the carbon ion formed after the deprotonation here will be more stable, because that can flow either way of this center, isn't it? So these protons will be the more acidic ones. Then we can observe the proton abstraction via ethoxide in this way. The oxide will attack at this proton and this CH bond breaking will happen, and the electrons from CH bond will move to this carbon-carbon bond, and in turn you will get this oxyanion formation. Okay, so yes, this stage is showing the curly arrow pushing correctly. Then in the next stage, if you see what is happening, the electron rich oxygen is pushing its electron pairs, and in turn this double bond in conjugation is attacking at this electrophilic center. Why is it electrophilic? Because of the presence of this electronegative chlorine atom, isn't it? So it will readily accept the incoming electron pairs and knock out the chloride. So again, you can see the flow of electrons starting from an electron rich species to an electron deficient species. And that is why you can say that stage 2 is also showing the arrow pushing correctly. Then after this step, you get this product. Okay, and then in stage 3, this product is subjected to hydrolysis, and by ester hydrolysis you are getting this carboxyl functionality in the stage 3. So in this stage, what is happening, let us see. So if we move from here, the electron rich oxygen is abstracting a proton from the acid. In turn, this OH bond is breaking, and the electrons of this OH bond is moving towards the carbonyl group, and after going moving the electron to oxygen and after coming back, this particular carbon-carbon bond is breaking, and as a result you are getting an enol here after eliminating water molecule, carbon dioxide molecule. Okay, so yes, again in stage 3 also we are moving electrons from electron rich center, leading to electron pair donation to this acidic proton, and then after breaking of this OH bond we are eliminating carbon dioxide, and this particular bond breaking electron pairs are moving towards this carbon carbon bond. So this particular stage is again showing the correct flow of electrons. Okay, so we are left with the last stage of stage 4. What is happening in this one? Let us move one by one. If we move from, let us start from here, okay, or maybe from here, where the electrons are moving from the electron reach double bond. So if it is moving from here towards the oxygen, we in the next arrow are pushing this proton towards this oxygen. But this oxygen in this water molecule is having lone pair of electrons, which is electron rich. So will it accept an electron pair like it is showing in the stage 4? Okay, in stage 4, what is it showing? The electron pairs after breaking of this OH bond, it is moving as a hydride to oxygen atom, which is not acceptable, because the if electrons are moving towards this electron rich oxygen atom, it will create a electron repulsion destabilization. Okay, so we can say that in stage 4, the curly arrows are not showing the electron push correctly. Okay, so after analyzing all the stages of this mechanism of synthesis, we have arrived that stage 4 is the wrong option here. This is the long description for the answer. You can see that, like I said, the proton in the stage 4 is leaving as a hydride towards the electron rich oxygen atom. Okay, so stage 4 will be the correct option. So with this, we have arrived at the last question of today's tutorial. So let us revise the questions which we solved today. Okay, we started with a summary of kinetic versus thermodynamic control, where we saw that sterically bulky bases lead to the formation of kinetic controlled product, whereas sterically less hindered bases lead to the formation of thermodynamic product. And that concept keeping in mind, we started with the first question: which of the following is the structure of the most stable enol of 2-methyl pentane? Where we talked about the factors which decide the stability of enol. What were those? Number 1, it has to be the most substituted one, and number 2, it may have stabilization either via hydrogen bonding or maybe conjugation. So by analyzing the options, we saw that option A was the correct answer. And then in the next question, again we solved a similar question where we had to pick up the most stable enolate possible for 1-phenyl butane 2-one. And in this particular question, we not only choose the option which had the most number of substitution, we also chose the option which was having less steric hindrance. Okay, that is why we place the alkyl and aryl substituents on different directions, thus getting this option C as the correct option. Then we moved to the screening of the stable enol form possible for this dicarbonyl compound, and we saw that out of these two options where we were getting the most stable double bond, the one where we got stabilization via hydrogen bonding, which is this particular option, we chose this option as the correct answer. Okay, and after that we tried to solve this question by looking at the mechanism of aldol condensation, and we saw that out of these 4 options, only option A was giving us phenyl vinyl ketone as the final product. So here we discussed the mechanism extensively and we chose option A as the correct answer. And then in the next question we looked at the various stages of a reaction mechanism for alpha bromination of methyl ketone, and out of these 4 stages we chose stage 3 as the incorrect one, where electrophilic bromine was attacking a highly electron rich double bond. Okay, and then the next question was quite similar as question number 1, which you may have solved already. And in this one, we chose option C as the correct one, because it is not only giving you tetra-substituted carbon-carbon double bond, also it is placing the bulkier alkyl substituents in the anti-fashion. Okay, that is why option C was the correct answer for this question. And then again a similar example like question number 3 we solved for this particular dicarbonyl compound as well. Not only the most substituted double bond we formed, but also we observed the hydrogen bonding stabilization. Okay, and after that we moved to this aldol condensation reaction, where out of option C and D, we chose option C as the correct answer because E isomers are more stable than the Z isomers due to less steric hindrance. Okay, and after that, in this particular question, we went through the mechanisms which all these four reactions should follow, and we arrived that in option C only the correct product was formed. Okay, in presence of this less steric bulky base, we observe the formation of thermodynamic product, the thermodynamic enolate, and this was the correct option for this question. And lastly, we again solved a mechanistic question where we had to screen the incorrect flow of electrons in these four stages, and stage 4 was chosen as the correct answer because it was showing electron pair flow as in the form of hydride to this oxygen lone pair containing water molecule. Okay, so stage 4 was chosen to be correct answer. So with this we have arrived at the end of this today's tutorial. So this week's topic was relatively easier, so questions also I guess were very easy to solve. So in the next week we will again solve more questions on this topic and more condensation reactions via enolates chemistry will be discussed in the next week's video lectures and also in the next week's tutorial questions. Okay, so I hope everything was to you. Thank you all for joining. Okay.